So today we'll be doing section 13.3 and 13.4. 13.3 is arc length, so that can allow us to find the length of a curve. And then 13.4 we do some cool stuff. We're going to check, just to explore motion in space, just a path of anything. It could be a golf ball. It could be any type of motion throughout space. We'll create the formula. We'll derive the formula together. Put the formula up here, and then we'll work some problems together from the practice set from the textbook. So hey, for length of curve, I thought the first curve we can get the length of. Let's get the length of a helix. The formula is we're going to take the integral from a to b, the magnitude of r prime to t. It's almost like you can think of it as the integral. This represents speed. Magnitude of r prime to t is speed. But we're going to take the integral of that. So they'll give you some vector curve. I thought we'd start with, let's start with one of those, a circular helix. I'm thinking, all right, how about cosine t, sine t, t. And let's just take this thing from 0 to 2 pi. So I'm going to find the length of this curve, which is also the arc length with those limits of integration. Find the length of the curve. From t equal to 0 to t equal to 2 pi. So we'll definitely set up the two limits of 0 to 2 pi, right? But the first thing we need is r prime of t. So let's start with that. What's r prime of t? We call that the tangent vector, right? What would be the tangent vector for this? Hey, you don't have to draw a picture, but to get a sense of this picture, isn't that the circular helix, as I mentioned? Which axis does it spiral? X, Y, or Z? Can you tell? Yes, I heard it, the Z axis, everyone, right? So it's like I'll hide this. Ever see that circular relationship? It's like, oh, this curve travels on a circular cylinder. X squared plus Y squared equals 1, right? But then the Z component just has a variable t. Just as t increases, the Z component is going to increase. So it's just going to spiral up the Z axis. That's what that would look like, right? We just made a quick sketch. We're like, look at this thing just going like this. We're only going to go from spiraling from 0 all the way up to 2 pi, right? So it won't go too far. 2 pi is about 6.28 or so. What's r prime? Let's derive cosine of t.
Negative sine.
Negative sine of t. Let's derive sine of t.
Cosine.
Cosine of t. And let's derive t.
1.
All right, so there's r prime of t. Now, we're going to write out the magnitude of r prime of t. Okay. So you're going to notice with this problem, everyone, we will be able to solve this. We will be able to solve this problem without the calculator. You do it without the calculator. This length of curve of this helix here. I'm going to put the big square root, right? All right, what's that squared?
Sine squared.
So
T
the negative squared becomes positive, right?
Mm-hmm.
So I squared that component. This squared.
Plus cosine squared t.
And then 1 squared is
1.
boom. And we'll put this in the integral. We'll go from 0 to 2 pi, but look at that carefully. Before we put it in the integral, can you simplify it?
Yeah, square root of 2.
So let's see this. That's the trig out any sine squared t plus cosine squared t is 1. So you got square root of 1 plus square root of 1, or square root of 1 plus 1, which gives you a square root of 2. Does everyone see that? We're saying this was 1. Oh, so now this problem got really, really nice. I'm going to put this now in the integral. Go from 0 to 2 pi, square root of 2, dt. This will be the length of the curve. Easy integral for us to solve there. Not every problem so easy. There's going to be some. I'll reference them from the textbook. Even in directions, they'll say, find the length of the curve, correct to 4 decimal places. They'll set you up to use your calculator and perform the definite integral because we wouldn't be able to manipulate that problem. like we did here. You know, when you deal with radicals, sometimes they can be neat. Ah, I got neat. Other times you get an expression that we can't use just to use something to solve. What's the integral of square root of 2?
Square root of 2t.
Go from 0 to 2 pi. Okay, 2 pi times square root of 2. Minus, you plug in a 0 and you just get what? 0, so I wouldn't even write that. There's the length. So this is a cool section. Up until now, it's like you say, find the length of some curve. All we knew up till now was what, edge of a circle? Like circumference or an arc of a circle? Stuff we did in geometry class. But now we can find the length of any curve, which is kind of calculus. So just think of like a ball being thrown. You're like, holy cow, we can actually find the length of that. If that ball got thrown from here to there, we can actually stretch that out and see what's that long length of that pass. If it was a football or baseball being hit, right? You're thinking of, who's that from the Orioles? Is it Davis? Who can smack the home runs? You're like, man, I can get the length of that ball. As long as we have a vector function that models that path. Now let's do another one, but this time I want to do a circular helix again. Okay, let's have it go down the y-axis. Okay, 3 cosine of 2t, 4t, 3 sine 2t. Get all this. This time, everyone, let's go from t equals 0 to t equal pi. Let's find the length of this curve. Find the arc length from 0 to pi. That's also a circular helix. Even though this has 3's in front, and this has a 4t, you can still suck in this right here. Just check it out real quick. 3 cosine squared of 2t plus 3 sine squared of 2t. I just want you to explore this. Isn't this on a circular cylinder, the path of this curve? I'm just looking at the x and the z components and just looking at them. And if I factor out the 3, what do you now have?
Cosine squared 2t.
Right? Oh, and I didn't square this, I apologize, so I'll square both of those. There's x squared plus the z squared, and let's just see what it turns into. I factor out the 9, and you got cosine squared of 2t plus sine squared 2t. And is that equal to 1?
Mm-hmm.
Great, so this is equal to 1. 1 times 9 is equals 9. So I just want to point out, this again, this circular helix travels on the surface of a circular cylinder. It's just going to have a radius of 3, right? X squared plus z squared equals 3 squared. I just want you to explore that. We'll do the math. But you can say, oh, this thing, well, which axis does it spiral down? It goes down the y-axis, doesn't it? Because that 4t. So we're just talking about some helix that goes from like 0 to pi. Right? We have to start at just a rough sketch. It's like, okay, there goes this curve. We'll see how long it is. Okay. So start it out. First thing, get R prime. Be careful with chain rule. What's R prime of t?
So that should be 6.
6.
So negative 6 sine 2t.
Negative 6 sine 2t. Very good. What's there, 4t?
4.
Hear this? 6
Cosine.
cosine 2t. So far so good? But again, watch. You'll be able to simplify this thing. You get the final solution even without it again. But after this problem, let's look at one where it's like, okay, we can't simplify it. Let's use calculator. All right, what's the magnitude of our prime d? my goodness. Whoops, let me get the square root ready. What is this squared? You gotta square that -6 too. 36 sine squared of 2t. What's that squared? 16. And what's this squared? 36 cosine squared. So before you go pulling out the calculator, setting up the integral from 0 to pi of this radical, see if you can break it down.
Square root of 52.
Okay, very good. You notice that 36, you can factor out of this sine squared of 2t plus the cosine squared of 2t. If you see that ahead of time, you don't have to show all this. I just wanted people to see why you're getting the square root of 52. Because this right there, once again, is just the value 1, right? You get the square root of 36 plus that 16 square root of 52. Or if you want to simplify it before you put in the integral, you can, but I'm going to leave it square root of 52. Maybe just simplify that at the end. There it is. Ooh, again, it got really neat. I'm going to go from 0 to pi. What's the integral? Square root of 52t. Multiply by pi, you get square root of 52 pi, or what's that simplified?
2 root 13.
2 root 13 pi. Excellent.
Don't do yet.
That's right. Anyone try this one? Find the length of this curve. You get, all right, t. Hey, I'm thinking from the textbook. It's got a t. E to the negative t. And t to the negative t. The limits? Can you find the length of this curve from 1 to 3? Well, that's not a circular yoke. Find the length of that curve. Just be careful with those derivatives, right? What's our prime? What's that derivative?
1 negative e to the power negative t.
Chain rule, right? What rule do you need?
Product.
We need product rule. See the t in front of that e to the negative t? So first, derivative second is a negative e to the negative t. Plus the second times derivative t, which is just a
Just 1.
1. And of course you could rewrite this as negative t e to the negative t, right? Root of 1 squared is,
1
what's this squared?
negative
E to the negative t times e to the negative t. The negative times the negative is a positive, right?
it's e to the negative t squared.
You get e to the negative t. And you multiply another e to the negative t.
There's a
Can't you add these exponents because you got the same base?
Yeah.
So you could think of it as e to the negative t parentheses squared, but we could add these. And what's negative t plus negative t?
Negative 2t.
I'm going to write it that way. Of course, you might be sitting there going, well, can't I just, I'm going to be hitting this on a calculator. Can I just do that? Yes, you can, but I want to write it one more time for you in case you're like, isn't that just e to the negative 2? And it is. Because you can, they have the same basis, you can add the exponents. All right, plus, what's this last one right here? Ooh, I'm just going to have to put a parentheses around this, right? Negative t e to the negative t plus e to the t. Close the parentheses and put the squared there. You don't have to expand that right now because we're going to be hitting this on the calculator, right? Does anyone care that?
Isn't it e to the negative t variable?
Oh, you're the best. Right on. Thank you. He's like, don't forget that little negative t right there. And I'll write this again because we will be exploring this with our calculators. Negative t e to the negative t plus e to the negative t, and then we're going to square it. So now we can put this in a what? Integral. What's the limits? 1 to 3, and I'll put my dt, but calculator. That's what the TID 3 or 84. Was it Math 9? If you got an old one like mine, then I have to write an integrate, type it all in. If anybody needs assistance, put this in on the calculator. Go right ahead. This is what the TID 83 can do. Square root, your calculator, I'm going to put some parentheses. 1 plus e caret negative 2t plus parentheses negative t times e caret negative t plus e to the caret negative t. And you got to square that, right? It's like all that squared.
We need a couple more parentheses, I think.
Right there at the end. I can make this one bigger so one can see this. That would close out this. Then I raise this to the what? All that squared, right? Then you write comma t, comma 1, comma 3. Using Math 9 off the TI-83s, 84s. You don't have to use t, you can use it next, right? We just want to make sure everyone gets the same value. And if you don't get the same value, don't worry. Maybe after class we can just check with someone else's calculator. Maybe missing the parentheses like you're saying. You gotta be very careful of it. Let me get it. What'd you get?
I got 2.045.
Anybody else get that? 2.045 is the length. Reach it up. Good job typing this in there. Just being careful with all the parentheses. That's the older models. The newer models let you, with the math print mode, you know, get you actually put those, that's the integral symbol and everything. Pretty cool. That's like an old TI-83 model. Can I erase? All right. Hey, one more of these. Then we'll do 13.4. We'll do motion in space. This is number 2. But again, because it's number 2 out of the textbook,
What the page number, Professor?
yeah, this one I think you can do without the calculator. We'll see. We'll see what they got. They've got 2t, t squared, and 1/3 t cubed. You got to go find the length of the curve. From t equals 0 to t equals 1. All right, what's R prime?
2t and t squared.
Okay. What's the magnitude of R prime? 4.
4 plus 4t squared plus t to the power 4.
So before I go jamming this in the calculator, draw examine that? Can you simplify that?
Yeah, so
In
that's.
fact, I'll write it from the highest power to the lowest power. Can we factor that?
Yeah, that should be like t square plus 2 whole square.
We'll put that. T
Square
squared plus 2 times another t squared plus 2. So you get this,
whole square.
which I can simplify to what?
T square plus 2.
All right. Can I go with that? Cool. And if you want to put the bars here and go, okay, it would be the absolute value of that. But we're still going from 0 to 1. This is the first time we got a problem with no radical. No radical in there. Oh, what's that become?
1/3 t cubed plus 2t.
From 0 to 1. 1/3 plus 2 is. Yes, 7/3. Having a great job at that. We'll now do 13.4. And I just want to point out, hey, before we move on here, Aiden, I liked your question about like, why is this, the why part? Why is this happening? It's explained briefly on page 853, but they do reference section 10.2. That's what Art was mentioning, something from calculus 2, dealing with the actual arc length and curvature. So in this case, once you have that, this is what they had. I just want to point this out before I move on, because I like this question. And I'm referencing section 10.2 from the textbook. They got length is equal to this. F prime of t squared plus g prime of t dt. Okay, I got all the parentheses there, right? Cool. They just put a name tag, but it's stemming from that section that's allowing us now to, as you can see, like a connection there, is turn this into this vector r prime of t. This is just what? dxdt squared. What's that? dy dt squared. A to b. But now we can think of that as, oh yeah, this is the derivative of some x component, that's the derivative of some y component. That happened, that f and that g right there, and that's where we can actually think of this as coming about. But it does, I know it's short, and it's a little bit too quick there on page 853, but they are referencing section 10.2 on there. All right, when this is motion in space, let's derive this formula. So we're going to start with, oh gosh, just the gravitational pull. Sound good? So you and I are going to derive this. So don't ever think like, if you're worried about memorizing this actual motion in space, R of t, for any path today, you can always derive it yourself. It's not that bad. Let's just start with acceleration. This will be cool. This will be the derivation. How about, I'm going to put negative g, all right, just on the j component, right? There we go. Right, due to acceleration, there we go, we got negative g. Let's go to velocity. So we got to integrate, true? What's the integral of a negative g with respect to t?
No.
Oh, that'd be derivative, right?
No, that's
So that's like a negative 9.8, and I got to take its integral.
so negative gt.
I'll put negative gt on the j component, right? But isn't there a constant?
Yes.
Okay, so I'm just going to put a plus C over here. Now, all we're trying to do is get the RT. We're almost there. Almost there. We're at velocity. We only get the RT. And this is in section 13.4. This is motion in space. And once we derive this, we'll work out a problem. All right, so in this constant here, I want you to think of this constant as the initial velocity vector. That's what it is. It's the initial velocity vector. So I'm going to put V of 0 for the constant. That's what the constant is. Now I'll go off to the side. Let you and I talk about this V of 0 right now. I'm just going to draw a picture. And when thinking of initial velocity right here, the initial velocity vector, can we think of its two components, x and y? What would the x component be? It'd be the magnitude of the initial velocity times cosine theta. And what would this component be? It'd be the magnitude of the
Y component.
yeah, the initial velocity vector times
Sine theta.
sine theta. So I'm going to write that here. Except now I'm going to write everything in terms of, I'll just switch from I was using standard basis form. I'm now going to write this in component form, okay? So what's the x component there of this velocity vector?
Initial velocity cosine theta.
And I'll even write it here before I change, substitute it in there. And when I'm saying this initial velocity vector has these two components. VO cosine theta and V naught sine theta. Now notice, if this is going to be the first time, I'm just not going to put vectors on it. How about from here on out, let's just call this initial speed. We'll write V naught without a vector on it. That way it's a scalar. So that's what I have. You know, the magnitude of V naught would be the initial speed, right? So I'm just going to put a initial speed, cosine, sine, and now I'm going to rewrite this whole thing. All right, what's in this component? Yeah, V naught cosine theta. What's in this component? Don't forget about that. You'll have the V naught sine theta minus a GT. We got one more step to go. We'll have RT. Did everyone see that? So it's all based on this. This was the initial velocity vector. I'm calling this right here just the initial speed. I'm just not putting any symbols on top of it. That's the initial speed. So, one more step, we'll have it derived. What's R of t? This is the formula we use over and over and over again today. What's the integral of that respect to t? Cosine theta times a t, right? This throws people off, but aren't these all constants?
Yeah.
Yeah. That's like some at 62 degrees. That'll be like 55 meters per second, right? And we're just taking the integral with respect to what variable? T. That's the only variable we're integrating this with respect to. All right, what's the integral of that then? V naught sine theta
T.
t. Now what's the integral of a negative gt with respect to a t?
So minus g divided by 2 t squared.
T squared over 2. There it is. Hey, what about the constant? I mean, okay. Then you say what? Plus r of 0, right? There's your constant. So if you want, how about, because some things today may be thrown from a height, not everything's thrown from the ground, right? So we can just put plus an h naught in this component right here. That's what I'll do. I'm just going to add a little h naught right in there. But then when you just derive this thing, when I write it over here, I'll leave it up all class. I'm going to write the same exact thing, except I think here I'll put plus an h naught, because this thing may be thrown from what? Not everything's thrown from the ground. Some things are thrown from a cliff, from the top of a battleship, etc. So I'm going to write it here. R of t, V naught cosine theta t, V naught sine theta t, minus 1/2 gt squared plus, I'll put h naught in case it's thrown above the origin. Metric, we'll use 9.8 for G. US customary units, we'll just use 32 for G, right? Depending on the units they got. Good to go? Cool. Feel free to just start there, any problems. That's just two-dimensional, right? There's one problem, I'll make sure we're working today. I saw there's one problem in the textbook that they had it in X, Y, and Z components, and you're okay, then the Z component can represent the height. Right? We can think of that as something being thrown, think of a pass being thrown off to the side or something. Okay, so here's the first problem we're going to deal with. Motion in space. We did derive it, we've got it. This was a pass thrown that went in a football game. It was December 3rd, 2015. That was the last play of the game. So it's the old, Hail Mary? And if you wonder which two teams are playing, this was Packers versus Lions.
Oh.
Maybe you've seen this play, but it was a pass by Aaron Rodgers. I mean, he's way down the field. So this is what happened. We're just going to throw a Hail Mary. The angle of elevation is 55 degrees. The initial speed was 25.4 meters per second. What was the distance down the field that he threw this thing? And when he launched this thing, it was, I'm going to put it in meters, 61.27 meters downfield, there was a receiver. So I'll just put in parentheses. There was a receiver standing 61.27 meters downfield from Aaron Rodgers. Okay. And he threw the ball from 2 meters in the air. So what's the initial height?
2.
So when he threw the ball, from 2 meters, just in height. So I'm going to start drawing this. X-axis, Y-axis. I'll start here at the origin. How high was it before it got launched?
2 meters.
2 meters. Boom. And he throws this thing. There's a receiver 61.27 meters downfield. Let's put a receiver down here. And let's say, I went for our math problem, that this receiver can catch any ball between 0 and 3 meters. The receiver can catch any football standing downfield between 0 and 3 meters. Why so high, everyone?
Jump.
You know, meters long, he can jump, right? He can jump pretty high. All right. Aaron Rodgers is the quarterback, going to launch it from 2 meters. Angle is what?
55 degrees.
55 degrees. Angle of elevation. Initial speed, 25.4 meters per second. Last pass of the game. The receiver can catch anything between 0 and 3 meters. So the question is, did he catch the ball? That's what we want to see. All right. I do want to point out, let me write it again, the receiver, or mention it again, I'll write it on the board. The receiver can catch any ball between 0 and 3 meters. Just think vertically. Okay. So I'll start with this. Let me write it all out. Now let's describe this pattern. RT. That's the X component. 25.4. You have to put the units. Cosine of 55 degrees times a variable 2. What's the Y component? 25.4 sine of 55. T minus, what's 1/2 of, we're going to use 9.8 for G. So I'll put minus 1/2 9.8. Feel free to put 4.9. And then t squared. Did I forget anything?
Yeah, plus the initial height.
This is huge, so be careful that not everything's thrown from the ground. Although we will do some problems today when it's thrown from the ground. This was launched from 2 meters in height. So right here in this y component, I'm just going to add up 2. All right. Yeah, there we go. Now, did the receiver catch it? Did he catch it? Where should we start? Yes or no? We've got to justify this. Did he catch the ball? Where should I start? I've got the distance x, right? You want to start there? It went 61.27 meters. What can I set it equal to? This right here. What can I solve for?
T.
T. So let's start there. We can actually solve for t and figure out the time it took for that ball to what? Travel all that way. I know it's going along that arc, but we can find the exact time that it took to get down there. 61.27 meters. Perfect. So I'm going to write 25.4 cosine of 55 degrees times t and set it equal to 61.27. So what's t? 61.27 divided by 25.4 times the cosine of 55. Make sure your calculator's in degree mode. And when this is interesting, those last problems we just did with arc length, we want those, if you're going to use a calculator, in radian mode. We go one section further in 13.4, looks like we're going to use a calculator, we're going to have everything in degree mode. So let me just make a note of that. Calculator, degree mode, for 13.4, and we're just going to have it in radian mode. Why didn't we have errors if anybody in here had to calculate in degree mode in the last section? Because we did most of those problems by hand, didn't we? We did most problems by hand. We only did that one with the e to the t. We don't need that in radians. Right? That could be in degree mode or radian mode. We didn't have any trig functions we entered into the calculator. Hey, what do you get for t? So 4.21 seconds. And he rounded it. What was before that? 4.2055?
2055505.
So I went over 4.2055 seconds, but he's like, hey, listen, it takes roughly 4.21 seconds to get down here. Okay. Now, how can we use that to help us answer this question? We know it takes 4.21 seconds to get to here.
Plug it in for T and the Y.
Plug it into the y component. Very good. Plug it into the t and the y component. And that will give us the height at that time. Sound good? Now let's do this, and let's discuss this. Let's say I get a number like 8. What's the answer?
No.
Whatever it's at, right? What if I get a number like 2.5?
Yes.
He caught it. So 0 to 3, he catches it. Above 3, whenever his head. Help me out with this. What if we get a negative value? That throws people off on the test.
No.
What if you get a negative value? What does that mean? What happened?
It fell on the ground.
There you go. Everyone's saying the ball fell down short. It would have hit here, and just, it's indicating that it would have rolled or something right along the ground. That's what the negative, which means incomplete, right? Excellent. And we're not worried about like the defenders, like interception. We're just saying, hey, this guy can catch this because in reality on this play, everyone did just jump. Everyone just jumped up. But the Packer receiver did get in front of everyone before he launched up, you know, like this. All right, so let's do that. You get your calculators? Let's put this in there. Put it there and put it here, and don't forget the plus what? 2. So what's 25.4 sine of 55 times, and when I just store this in my calculator to some letter like what? X? Do you do that? I'll store this number to X, and I'll go 25.4 sine of X minus, times sine of 55 times X minus 4.9 times X squared plus a what? 2. I'll type it like this into my calculator, but I stored this number without even rounding it to some variable like X. Cool. You know where the stow button is on the calculator? All right, what's the height? What's the height of this ball?
At like 2.747.
What do you don't think? Did he catch it?
Yes.
Yes! Catch! He caught the ball! Cool. And we'll play with this problem a little bit too, but does anybody want to see the play?
Yeah, sure.
Okay. Let's just see. It's cool. Doesn't take much time. We want to see this thing. Did he really catch this thing?
I'll turn the cam off for a second.
Is it far enough, that projector?